In any central force problem, angular momentum is conserved, am I right? Spherical planet of mass capital M and radius capital R and uniform density rotating anticlockwise about an axis passing through its center, okay, which is in the figure below. It is normal to the, I mean, this rotation is normal to the plane of the paper or something, okay, this rotation axis, okay, fine. The duration of a day on the planet is T. What do you mean by that one? Like, you can say T is the time period or something, roughly. Duration of a day, of a day. Okay, one day is T means one day means what? Okay, that is total time period of this, what is that? Rotation. Okay, fine. Now, what is happening is, I mean, he has shown nicely in the diagram, a small asteroid of mass M, okay, approaches above planet from far away with a uniform speed. Okay, when it is far away, it has uniform speed. Okay, along a straight line at perpendicular distance r1 here. So at perpendicular distance r1 here from the center of the planet. Okay, this path gets distorted by a gravitational field of the planet. Okay, and asteroid leaves with a final uniform speed v2. Okay. I mean, in this direction with a perpendicular distance r2. That means you have to fix this one as your axis of rotation. He's measuring all perpendicular distance with respect to this one. Can you see this one? You have to think of an axis of rotation which is perpendicular to the board, okay, passing through center of this big planet, okay. It is leaving with a speed v2, okay, along a straight line at a perpendicular distance r2, okay. He mentioned this r2, okay. It is observed that after passage of asteroid, the length of a day on the planet has changed by delta t. What is that delta t? That's what he's asking. Okay, I mean, you can see here, I mean, I feel that it may decrease its rotation speed, am I right? It appears so. Okay, fine. Day may be quite longer after this asteroid. Can I say like this? Is that okay? I mean, now you may get idea how to make Earth day quite longer, isn't it? Then I think all of our biological system will disturb, isn't it? We may need to take one more meal in a day if day is longer, isn't it? I mean, it is not as difficult as it seems actually. Okay. Now you apply conservation of angular momentum. Okay, fine. Angular momentum of m plus angular momentum of capital M, that must be conserved. Am I right? That must be constant. Okay, fine. Now, I mean, this is, I mean, now if I take any change here, delta L of m plus delta L of capital M, can I say like this? Change, that must be 0. Now what I do is, okay, what is the change in angular momentum of small m? I mean, with respect to this one, that is, what is that? MVR, can I say like this? Okay, M1 V1 R1, M2 V2 R2. Can I say like this? Final minus initial. Okay, fine. M V2 R2 minus M V1 R1. Can I say like this? M V1 R1. Can I say like this? What is this one? This is change in angular momentum of M plus change in angular momentum of capital M, that's equal to 0. That's what I'm trying to apply. I got this one. Fine. I got this one. This is quite quick. Delta L. But how do you write angular momentum of capital M? That's equal to I into omega. Just like mass into velocity. Isn't it? Because I mean, you need to connect it to time period, day and all. Am I right? You have to write I omega. He said, look at here. He mentioned radius, uniform density to write your moment of inertia. Isn't it? Fine. If it is not uniform density, you can't write usual moment of inertia expression actually. Okay. That's what is this one? 2 by 5 m r square. Okay. Omega is, I mean, it is rotating with uniform angular speed. What is this one? Omega is 2 pi by tau. I'll use tau for my time period. Okay. Fine. LM. Okay. Now look at here. Now, how do you find change in this one? The radius is not changing. Mass is not changing. Okay. This is changing. It's a kind of derivative expression now. Can you say like this? Okay, I'll use this delta symbol. That's better. Delta is better symbol. It's close to calculus. Delta LM. Okay, fine. This delta L capital M, that's equal to 2 by 5 m r square. It's a kind of derivative actually. What is this one? Into 2 pi. How do you take the derivative of 1 by tau? That is minus 1 by tau square into delta tau. You have to write like that. So I forgot to do that error analysis. Am I right? In error analysis, we apply the same logic. It's a kind of derivative that I have taken. Are you getting it? Delta LM, it is related to delta tau in this manner actually. Is that okay? Because one is reciprocally related to other. Is that okay? Suppose if LM it is proportional to tau, then delta LM proportional to delta tau. But when it is inversely related, this kind of relation will come. Even if you define L at one instant of time at tau 1, second instant of time tau 2, when you subtract, when you do that one, you will have some denominator term actually. Okay, you can argue, but right now I will see it as a what you call derivative term. Okay. Now what is this one? That is my delta L capital M, that's equal to minus 2 by 5, okay, m r square into 2 pi delta tau by tau square. Fine. I'll use tau as my what is that the time period. Okay, fine. Is that okay? That was the time period of that omega. Omega is an angular speed. Am I right? It can be it can be written as 2 pi by tau. Is that okay? Fine. See this one. Now this is equal to negative of this one. Can I just equate? M V2 R2 minus M V1 R1, that's equal to negative of this one means 2 by 5 M R square 2 phi delta tau by tau. Okay, he's asking delta tau 5 by 2 came. Do we have option? 5 by, I think you will get this one. Delta tau, that's equal to 4 phi. Can you see here? Delta tau 5 by 4 phi 1 by M R square. Okay, M into V2 R2 minus V1 R1. That's right. V2 R2, V1 R1. Okay, that works.